Progress.
Good morning. This is the annual control talk this is the annual control talk for the doctoral school of Alex Jimenez Romero, and he will present some of the last work he has been doing in the recent few months. Actually, this work there's a preprint who is not cited here in the archive, but you can find in IFE's publication webpage. The title is Mapping the Distribution of Seagrass Meadows from Space with Deep Convolutional Neural Networks.
Okay, thank you, Manuel. Well, yes, this is a project that we started long ago indeed, but I have been working on this recently. I have to mention that Tafer was also working very hard on this, so thank you. And this is also a collaboration with Pablo, and the supervisors are Tomas and Manuel. Okay, so well, as Manuel said, this project aims to map indeed not only seagrass meadows, but other habitats in the Mediterranean Sea from satellite imagery using deep learning. So first of all, a little bit of context, no? Well, many of you will know this already, but seagrass meadows are very important coastal ecosystems as they provide critical ecological functions. For instance, they contribute to oxygenated water and also to carbon sequestration, and they provide habitat for a large number of marine species. Just for you to make an idea of the degree of contribution of these seagrasses, for instance, Posidonia oceanica, which is endemic of the Mediterranean Sea, and is one of the most important species here in the Mediterranean, is able to sequestrate, to absorb, let's say, more or less 8% each year of the CO2 contribution of the Balearic Islands, of the emissions of the Balearic Islands. And this is more or less like 10 times the emissions that in a single year, all the cars, buses, and motorbikes, etc., emit, no, in Mallorca. So that's a huge contribution indeed. And well, unfortunately, as you might expect, global change is affecting the growth and survival of these ecosystems for different reasons. For instance, rising temperatures, eutrophication, massive anchoring, and a large etc. of things. Indeed, the ecologists have already shown that there are alarming decline rates for these ecosystems in the Mediterranean in particular, but also in other places in the world. And this has led to the United Nations to declare the urgency of protecting and restore these ecosystems and highlighting the need for high quality monitoring. Now the question is, okay, you have to monitor these ecosystems, but how can we do this? Because it's quite challenging as these ecosystems are underwater, so they are not very accessible. One option would be to just go there, snorkeling or scuba diving and taking some measures. This, in principle, should be very accurate, but you cannot do this in practice every day. And also, you can only cover a small spatial extent. Another option is to use photo interpretation of airborne imagery from planes, for instance. This is indeed done in other things, for instance, to build the Corinne land cover. I don't know if any of you know it, but this is a data set, let's say, of different types of land, like crops, urban areas, whatever. No, you can do this just by looking at pictures like this, but of course, for underwater ecosystems, this is not that reliable. No, and okay, you can cover a large spatial extent, but it's not reliable, and you cannot do this every day. You cannot use a plane every day, no, because it's impractical. Another option, which is the best of those, I think, is using a side scan sonar. This is a very accurate methodology. Indeed, you can, using these instruments, you can identify different species in the sea bottoms. So it has a very, very large spectral resolution, and you are able to identify, yeah, as I said, this kind of algae or this kind of, you can even see different spectral difference between different types of sands. So it's very, very accurate. And you can use this with a ship, no, to cover a large spatial extent. But again, you cannot do this every day, not every year, not every 5 years probably, because all of these are very expensive and time consuming. No? So recently, another option that is increasing in interest is to use artificial intelligence in conjunction with remote sensing data. This kind of data is basically, so what you do is basically measure the radiance that is absorbed or emitted from different objects. You can do this for a given area, no? And you can measure this radiance. And the idea to use artificial intelligence is the following. First of all, of course, you need to have a ground truth data set that is your reference for the objects you want to classify. No? So you need to know where these objects are and what these objects are. And then you can train an artificial intelligence model using the spectral data and this ground truth data set, so that in the end, just by having the spectral data, you can predict which objects you have there. No? This would be more or less the idea. Maybe it's better to see it with an example. This is quite common, just trying to identify 3 species from spectral data. In this case, this is an RGB imagery from planes, no, that are obtained from planes. So this is the kind of data you have. You maybe go there, and just by looking at the trees, you know, okay, this tree is this kind of species. You record with your GPS the coordinates, and you do this for I don't know, different places in the forest or whatever. And you use the RGB imagery, the georeference data, to train an artificial intelligence model that is capable of detecting these trees and identifying the species. No, well, this would be the results here. Some results are very good, like these ones. These are not that good, but I don't know. This depends on the data you have, the model, or whatever. No, but this would be the idea. So this is more or less what we have done, but for underwater ecosystems, which is more challenging. But I will show you that in principle you can do this. So exactly what we have done is we have used satellite imagery. So we have 8-band satellite imagery. So instead of RGB, we have more bands. Okay, and we also use the bathymetry, so the depth of each pixel. We know the depth of each pixel, and this is going to be used as one of the features of the model. Okay, I must say that the near infrared does not penetrate into water, so this is not providing any information. So we are going to remove this band, and we are going to use the bathymetry in the end. So we have 8 features. These bands, except for near infrared and bathymetry. So then we have a very, very large and extensive ground truth data set that was obtained through side-scan sonar. So it is very, very precise. We have a lot of species there, but as I will show you later, we will merge all these different species into 4 main categories, because if not, it's practically impossible. But in some places in which the sonar could not access, the data was obtained from field data, well, from field measures and photo interpretation. But the main data, so the main part of the data set is from side-scan sonar. Okay, here you have an example of what I'm saying. No, this is the kind of data that we have. I will show you later a better image. And of course, what we do is to train deep learning models to try to predict this distribution of the ecological classes we want to predict from the satellite image, as you can see here, an example. No, so we are going to use deep learning models based on convolutional neural networks, as are one of the most suited architectures for this kind of task. We are going to use 4 architectures that are all convolutional neural networks, and these architectures can be built with different backbones. So we are going to test 10 different backbones in total. Let's say we're going to train and test and deploy 40 models. Okay, so this is the data that we have. This is a very, very good data set. As you see, it's for the whole Balearic Islands, and it has a lot of resolution. So, okay, what we are going to do is, of course, to split the data into train, validation, and test. Here I just show train and test. So what we are going to do that is not common, and I'm going to explain why, is to select Mallorca's training and the rest of the islands, so Menorca, Ibiza, Formentera, and Cabrera, as test. Okay, this is not the usual thing. What you do usually is to perform an 80% goes to training of the data, and 20% goes to testing. And you take it randomly, no, to have samples of all the variability you have in your data set. But we wanted to test if just training here, our model is able to, let's say, generalize its learning, no, and predict good enough in other places. Okay. So basically, this is a 50-50 split. We have different species in the other islands that are not present here and the other way around. So this is indeed very challenging. We have also different, let's say, environmental conditions, sometimes different image specifications, different dates of image acquisition. So at the beginning, I would say, okay, if I train here, the results are going to be horrible in the other islands. No, this is what, I mean, this would be normal, but on the other side, no. If it's possible, for instance, if we want to classify Posidonia, Posidonia is Posidonia. It's the same plant, no? So I don't know. Let's see what happens. And indeed, as I told you at the beginning, for instance, something that I was very surprised is that the kind of sand in Mallorca is different in the dataset. It's categorized different than the sand of Ibiza, Formentera, and than the sand of Menorca. This is because of the side scan sonar can identify these spectral differences, but probably from the satellite you cannot, no? So there are these differences. Let's see how this affects in our model, no? So basically what I want to say is that this is very challenging. And let's see what happens. So, well, this is an example of what happens when we train the models, no? You have these learning curves and so on. So the models are training properly. They seem not to overfit. All is going well. This is the same for all the architectures and all the 40 models. And in the end, we can convert the performance of the models on the training data set. So what we see is that UNet and LinkNet, no, for all the different backbones, outperform these other two architectures. Okay, so we focus on those two, and those two have very similar performance, but LinkNet, this one here, has fewer parameters. And then we are going to choose this one because then it's less prone to overfitting, and the micro.
When you say that when you test the model,
yeah,
so you use satellite images of Menorca and Ibiza
yeah.
For the testing, and then the result is contrast with what?
With the data.
With the data of sonar.
Yes.
Okay.
Yes.
So basically, the truth is given to you assume that the data of sonar is the truth.
Exactly.
Because it's more accurate and whatever.
Yeah. There are also, for instance, the data we have from sonar come from two different expeditions. I don't know. Okay. One was around 2000 something, and there was an update in 2019 or something like that. So it's more recent. But because I've seen a lot of this data, both of the data, in this update, they just updated the shallower parts. I think maybe, I don't know, up to 10 meters depth or 15, but not the whole data set.
So you can only test on those parts, I guess. No? In the other ones, you cannot test because you have nothing to contrast with.
No. We have the data, but maybe what I'm saying is that some data is very recent, but some data maybe it's from the 2000s.
Right. That might be, and you don't know if
it has changed.
If the prediction is wrong, it's because the data is wrong.
Exactly, you're not sure.
So you cannot really test.
We expect that it doesn't change a lot, but exactly, it could happen that you are counting as an error because we use all the data in a way, because we don't know if this pixel is from, I don't know it, but I've seen, let's say, the evolution of the data, and I suspect that they didn't, but I don't know it with certainty. But yes, it could happen that some errors are not errors. I've thought about this. So, okay, and then we select this model, no? Well, this model that are indeed 10 models yet, no? Because you have this architecture with 10 different backbones. So we compare all these models. So for instance, with UNet, UNet is a well, the architecture of UNet is something like this, no? And each of these blocks are convolutional neural networks blocks that you are reducing. What you do, the images go like this. From these blocks, they are reduced, let's say, and then you scale up the image, and also you have skip connections. Well, it's a very complex architecture. But each of these blocks are convolutional neural networks, and these convolutional neural networks, you also have different architectures for these ones. So each of these blocks can be, for instance, ResNet 34, ResNet 152, EfficientNet, blah blah blah.
Different networks.
Neural networks, yeah. So because this is like neural networks of neural networks or whatever. Yeah. Exactly. You can choose. Yeah, it could be like different parameters or as you want to see. Yeah. So we use LinkNet. That is the main. It's not this architecture. It's a different one with all these convolutional blocks. So something we observed, more or less, was a kind of emergence of specialists. What we want to say is that some networks work better in segmenting some specific classes. There is not a lot of difference, but this was like curious, no? So then we decided to develop a consensus algorithm to see if this algorithm was more robust and provided more reliable results. And indeed, we can see that if we take all these models, we predict, and in the end, we apply this consensus algorithm, and now we go to the test, which is the other islands that blah, blah. We observe that these are the best results. Okay? So indeed, this way of doing the final prediction provides more robustness to the model. So we have the bottom model again. So now let's see a little bit the
numbers is percent.
Yeah. The maximum would be 100%. The maximum performance. Yeah, exactly. It's very bad. It's very bad. I'm going to talk about this. Yeah. I will. So yeah, well, just like take this in your mind because I will talk about this later. So okay, in general, this would be the results in the training dataset and test dataset, no? For a lot of different images, covering the whole Balearic Islands. So we observed that, of course, in the training set we have very good results. In the test set we have less good results. This is expected, but I mean, if we had done the usual 80-20 split, the results in the test would be better, of course. But I mean, they decrease quite a lot, but it's very good because of the challenging the problem is. I don't know how to explain this. And anyway, this is way better than random prediction, or in this case, using the majority class. Let's say all is Posidonia, for instance. No, so it provides quite good results. And indeed, I have no time to explain this, but IOU, intersection over union, is the best metric to see the performance of these algorithms. No, and it is very challenging to beat this metric. I don't know how to say it. So we see that what is usually understood for acceptable IOU is 50%. If you have more than 50% of IOU, the machine learning engineers that work on these kind of things say, okay, it's acceptable. So I will show you some visual examples of why. But here we see that in the test set, so going to Menorca that has different species, blah, 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 some of them are not acceptable, but most of them are acceptable. So for me, this is a very good result. Here you can see also another thing we did is, okay, now let's go to in the train or in the test for each image. Let's with the predictions we have done, let's measure the area of each class, Posidonia, Sand, and let's compare it with the true area, with the area in the ground truth dataset. for that image. You do this for all the images, and you see that, of course, in the training set. So they are very similar, and in the testing set are not that bad. Of course, this is log-log, so these small differences are not that small, maybe, no? But they fall in this line. So the predictions for the extension of each of the classes are quite good even in the test set, except for other green plants. Well, I will explain why later, but the good thing about this is that this allows us to measure the typical error that we can make when predicting the extension of Posidonia, for instance, so that now if I want to go to Italy, make a prediction and measure the extent of Posidonia, I can at least assume this error. So I think this can be useful because, well, I should have said this in the context maybe, but there have been works on using artificial intelligence with satellite images to predict Posidonia, for instance. But what they have been doing until now is they go to a given bay, no, Poyensa, let's say. You have one image there, you divide the image in train test, and you show that you have 95% accuracy. Yes, okay, but if I did this and I went to Alcudia and I had 50% accuracy. So this is not working. And what I want to show here is that if we give these neural networks or whatever enough data, you can gain a little bit of generalization. So in the end, this can be useful, kind of. So it's very challenging, but I think we can achieve this. So about the IOU and what I want to show you, this is an example of the in Poyensa. This is the Bay of Poyensa. This is in the training data set. This is the ground truth. This is the prediction, which are basically the same, no? Are very, very good. It's very, very good, the prediction. This has an IOU score, a performance of 90%, okay? And this is Formentera. This is in the test set. This is the ground truth, and this is the prediction. Also, you could say it's very, very good. If you look it carefully, it's not that good as this one, but it is very good. And this is around 80% IOU. So there is a huge decrease, but still the prediction is very good. So to have 90% IOU is like basically doing it perfectly, no? Then when you have 80% IOU and you look it, you also would say it's a perfect prediction already, no? This not happens with 60% IOU, but for instance, 60% IOU is not that bad. For this reason, 50% is considered acceptable. Okay, so now I will explain you now this plot, but what I want to show you is why the model is failing that hard in other green plants. Okay, so first of all, let's understand this plot. So here I'm plotting for each band that we have, so coastal blue, blue, green one, green, etc. The response values, so the reflectance of each class. For instance, so let's focus. Imagine we only had one band, like green one, to predict, just this one. So what we would like is that the distributions were very different and they were separated, because then it's easier for the model now to say, okay, if you, like the very easy thing would be if you are into this value and this other value, you are sun. If you are into this value and this other value, you are the other class, no? So we want these distributions to be separated and different. We can approximate this. So what we did is to compute the average difference among each pair of the distributions for each band. This is what I plot here. And with this, what you can see is that these three bands is the ones that provide more information, which are blue, green one, and green, then coastal blue, and then yellow. Red H are basically like near infrared, I think this is, so they do not provide a lot of information. Okay, of course, this is a very trivial simplification, let's say, because the neural network is going to use this in a higher dimensional space to do the prediction and all that, but at least so that we can understand something or have some insights, I think it's useful. And indeed, we are going to use this to understand a little bit more why it is failing that hard in other green plants. So this is the confusion matrix of the training set, and this is the confusion matrix in the test set. Of course, we would like to have 100% in the diagonal. This is similar to what it happens in the training, but in the test, we have something different. And what we observe, for instance, in Posidonia, we have very good performance, no? But for other green plants, what we observe is that most of the other green plants, that indeed are very few examples, but anyway, most of those examples are predicted as Posidonia, no? So why, no? We know now what, which is the type of the error the network is doing, but what we can do, similar to what we did here, is the following. For the Posidonia, this is for each class, sorry, we compute the Wasserstein's distance between the distribution of the response value in the training set and in the test. We would like to be the same, no? So the idea is that the reflectance of light, let's say of Posidonia, is the same in the training set that in the test set. Then you can predict it. If not, it's impossible, no? This would be the idea. So what we observe is that for Posidonia, this is true, no? This is how, so the lower the value, the more likely are the responses of that class in the training and in the test. So for Posidonia, the Posidonia in the test is very similar to the Posidonia in the training. Then for this reason, you achieve this very good prediction. But for other green plants, what is happening is that other green plants in the test is more similar to Posidonia in the training than to its own class, other green plants in the training. So what is doing the neural network in this prediction? I mean, it's what she has to do. I don't know what to say. It's normal that she's doing this. Now the question would be why this is happening. I don't know. What could be happening is what Pera said, for instance, no, that these other green plants in the 2000s were there, but now, I don't know, I don't think so, but maybe there is Posidonia. Also in the other green, I mean, this is a very complex thing because in the other green, we have a lot of classes that are algae on Posidonia with stones, algae with Posidonia with sand, sand with Posidonia, sand with algae. So we have a lot of mixed class that we, I don't know, if it had Posidonia, maybe we put it as Posidonia. I don't remember exactly, but these kind of mixtures could also be doing this kind of stuff, no? So at least I understand why other green plants was being predicted as Posidonia. It makes sense indeed, that prediction. Okay, whatever. Then this would be more or less the results. So in the end, just to summarize a little bit, what we have is a model that just being trained on Mallorca, it's useful to provide the distribution of these classes in Menorca, Ibiza, Formentera, etc. It's not perfect, but it's useful. So what we have done, and we know the errors the model is committing. So what we have done in the end is we train the model with all the data from the Balearic Islands, all this data, so that we have the most updated model, no? So the best we can do. And we provide this to the scientific community. No? If anyone wants to use this is open in a GitHub and Zenodo repository. You can download the models and do what you want. This would be the results of this model, no? And I compare this with the ground truth data and with the model trained with only Mallorca. And yeah, that would be it. Then we can go to Italy, for instance, go there, measure, predict the distribution, make the measures of the area, for instance, put these errors that we have measured as you cannot put less of these errors, more it could be. And that's it. This is the best you can do by now, no? This would be the idea. So, I don't know, just to show you a little bit some things. This is Palm, I think. So this is in the training set, in the original training set. All the images are in the training set of the full data one, of course. And what we observe is that the prediction is quite good. Of course, when you train with all the data, this is also interesting. So this has been trained only with Mallorca. And here, it is not doing it perfect, no? This has been trained with all the data. And it is doing this part better, no? So this is quite normal. In the end, when you provide more and more and more data to a machine learning model, it learns better. No? But But it's interesting because it's learning by having more examples from other sites also. No? Well,